This motion picture has been made to help you men who have chosen mechanical engineering as your profession. Perhaps you've considered the idea of working for a chemical company. Perhaps, like some mechanical engineers, you have wondered what a chemical company wants with men of your training. Perhaps you've wondered whether you'd be working for chemical engineers. Or maybe you can't see how a mechanical engineer would get very far in a chemical company. That's why we want to show you something of what goes on at DuPont, where your advancement depends more on your interests and ability than on your field of training. Keep in mind throughout this visit to DuPont that the chemical industry is a growing one, growing by leaps and bounds. Just to give you an idea, at DuPont, in the first 5 years after World War II, over $700 million were invested in the manufacturing side of the business. There are now more than 70 plants in 25 states. No one actually can tell where the end is. But we do know that every year, new and more complex products come out. New fibers, new finishes, films, dyes, plastics, agricultural products. Just a few examples. Before making any one of those products commercially, a mass of mechanical problems first had to be faced, appraised, and solved. And here's something important to keep in mind. At DuPont, mechanical problems are solved by mechanical engineers. The company does practically all of its own engineering work, right from the very beginnings of fundamental research. It not only develops process equipment, but actually makes a substantial part of it. DuPont men work continuously on ways to improve existing equipment. They design and build the plants, carry on the maintenance, and of course, supervise manufacturing. Let's consider the opportunities available to you here. Is research and development your special interest? Or machine design? Maybe you're the kind of a fellow who goes more for that. How about plant engineering, including power, maintenance, design, and construction? Or production supervision? Perhaps you lean toward this kind of work with its handling of people. Let's start with research and development. Some of the work is done here at the experimental station. A mechanical engineer in this field develops mechanisms used in making the company's products. His work may result in a massive piece of equipment like this, or in a delicate instrument like this one. There's never been a shortage of problems for research and development engineers. They run into the thousands, actually. They may lead to original equipment to meet new and specific needs, or to improvement of machines already in operation. Let's look at a few examples. These huge compressors are used in making urea from carbon dioxide and ammonia at high temperatures and pressures. Ammonia pumps like this can deliver about 100 tons a day. At these high pressures, machine work, alignment, and assembly are extremely important. Tolerances are severely narrowed as pressures climb. One of the secrets of this type of high-pressure work is the action of the pump plunger in the packing. Specification of the right plunger material is essential. High-pressure design calls for great pains to avoid stress concentration, such as might occur in sharp transitions at corners. Pulsations at high pressures cause rapid fatigue of materials and give rise to many design problems that fall strictly in the mechanical engineer's lap. Now here's a machine used in the plastics industry. It's called an extractor extruder. It melts plastic, takes the solvent from it, and extrudes it in one operation. Well, to adapt it to DuPont plastics, or to scale it up or down, called for studies in power requirements, heat transfer, and fluid flow. In other cases, engineers often design and develop equipment for use by DuPont customers. Here are two young engineers working to improve a machine that simultaneously forms and expands a tube of plastic material. Or a fellow may get into a project that requires work at super pressures. Here's a field that's really challenging, and young too. Behind a steel and concrete barricade, equipment can be tested at pressures far beyond those used in manufacturing today. After strain gauges have been attached to the test piece and the pressure lines connected, A mirror is placed so that an engineer can observe the results of the test through a periscope on the other side of the barricade. There will come a time when pressures far beyond those of today will be used. 20, 30, 40,000 pounds per square inch. These men are getting ready for the time when pressures even higher than this may become part of industrial practice. When a process or product worked up by chemists moves out of the lab, teams of mechanical and chemical engineers take over. For example, here you see molten nylon being solidified on a semi-works casting wheel at an early stage in the development. Many mechanical problems had to be solved before nylon was produced successfully. And naturally, mechanical engineers had a big part in solving them. Just how would you go about melting nylon chips at several hundred degrees Fahrenheit with as little decomposition as possible? Well, mechanical engineers designed and tried quite a few types of melting grids. Some of them didn't work as well as others, but they finally came up with a grid that did the job. And mechanical engineers designed a precision pump that works at pressures better than 1,000 pounds per square inch, but not before they lick the problems of gasketing, sealing, and materials. The hot melted nylon solidifies into filaments as it is pumped through holes in the spinneret that are almost too tiny to see. Naturally, that spinneret isn't a standard item either. It had to be designed. Nylon fibers are sometimes wound on these spools at a rate of 1,000 yards a minute. How would you go about winding yarn at that speed without any deviation in yarn tension? Sound like an interesting problem? The fellows who developed this traversing mechanism certainly found it so. Let's move on to this petroleum laboratory to see another important part of development work, activity devoted to improving existing processes and products. Here, engineers are constantly trying to improve the chemicals DuPont sells to the petroleum industry. The road to any kind of improvement is filled with facts, and these engineers are getting the facts by studying the action of lubricant assistants, grease stabilizers, and other petroleum additives. Here, engineers are studying exhaust condensates that indicate the effects of tetraethyl lead. Engineers study these things in the laboratory. They study them out of the road, too, in passenger cars, in trucks, through tests under various kinds of rigid control situations. The instruments in this test car indicate and graphically record information on such factors as horsepower, fuel consumption, speed, spark setting. That's the way mechanical engineers, working with chemists, arrive at conclusions which result in better and better engine performances. We have seen that research and development includes developing new process equipment and improving existing processes. It also includes design. The engineering department handles design work for most major projects. In some cases, it is machine design. In others, process equipment design. But always, it is the work of teams of engineers, mechanical, chemical, electrical, civil, and so on. Normally, these are men who make their careers in engineering. They work with engineers from the manufacturing departments to design plant equipment and machines. For an example of major design, how about this huge hypercompressor? It builds gas pressures from 450 pounds to 12,000 pounds in 3 stages. When these compressors were built, you just couldn't buy equipment like it. So DuPont engineers pitched in and designed their own. Or maybe you'd like to roll up your shirt sleeves on one like this. Adapt standard equipment, such as this blue gas generator and its control mechanism, to DuPont's ever-changing needs. Over the years, more than one mechanical engineer has thought hard on this one. There she goes. These are just a few of the problems mechanical engineers work with at DuPont. They are typical of the work in research and development.